Hey, you see salt? Hmm, not unless there's a mirror. Oh, of course. Today, I want to talk about differentiability and continuity, two of our most important properties in calculus and how they relate to each other. So, continuity. What's the deal with continuity? Continuity means that our function can intuitively means our function can be drawn with a single pen stroke if you're saying continuous on a set, right? That just one stroke of the pen on that set without lifting from the page, right? But this is sort of unrigorous, right? So instead, we if you want something more mathematical, we say, all right, at some point x equals a, the function is continuous if and only if the limit of f of x as x approaches a, meaning track the y coordinates of these points and the y coordinates of these points, right? So the two-sided limit, if and only if the limit from the left, limit from the right, they're both equal to the actual height of the function, right, at a, right? So if the value of f of a equals the limit that's being approached from both sides, then we say the function is continuous. So limits give a really nice basis for good rigorous definition of continuity. They also give a really good rigorous basis for the definition of differentiable, right? Limits define derivatives, and if that derivative exists and equals a real number, then we say that the function is differentiable, right? So here, when we see the limit exists, we're not counting infinity or minus infinity, right? We mean that it equals some real number, right? Well, it turns out it's nice to see in mathematics, you have two properties of the same type of object, continuous functions, differentiable functions. It's nice to see sometimes maybe a little visual representation. You might wonder, if this is the set of all functions, you might wonder, how do these interact, these properties, right? So you could say this is the, out here, say we have the set of all functions on the real numbers, right? And then maybe this is the set of differentiable functions, and then maybe you have this other set of continuous functions, and how do they relate to each other, right? Is the set of continuous functions properly contained inside the set of differentiable functions, or vice versa? Is the set of differentiable functions, is that properly contained inside the set of continuous functions? Or maybe a function can never be both continuous and differentiable at the same time, right? Or maybe the set of differentiable functions are properly contained in the set of continuous functions, right? These are all possible. That's the avocado possibility, right? Or maybe they're just sort of independent, right? Maybe you can have functions that are differentiable, not continuous, continuous but not differentiable, and maybe some that are both, and maybe some that are neither, right? So it's interesting to ask how these, whenever you have two properties of the same type of object, you ask, how do they relate, right? Do you have a diagram where the two circles are contained in each other one way or the other, or where they're overlapping some, right? And this is called a Venn diagram, by the way, right? This sort of diagram, and it's often a useful construct for this kind of scenario where you have two or more adjectives being applied to the same class of objects, and you want to think about how they relate. So here's the theorem, the big theorem in one of the big theorems in calculus, is that if f is differentiable at a point A, right, then f is continuous at that same point A. It turns out that it is in fact impossible for a function to be discontinuous at a point if it's differentiable at that point, right? So that's another way to say this, right? An equivalent way to say this is right? It is impossible for a function to be differentiable but discontinuous at a point, right? At the same point, right? That's another way to say the same statement. So this is a theorem in calculus, and in this video, I'm not going to prove this theorem. It's pretty it's pretty technical. It uses a lot of nice properties of limits, and it's in my textbook, right? So as actually a nice exercise. So I don't want to give away all the fill. It's a cute little fill in the blank exercise. So I recommend reading the section and trying to fill in the blank exercise in my textbook. So I'm not going to prove it here, but I just want to talk a little bit about the theorem. In particular, I want to say about something that is not true, a related statement that is not true. So this, if you think about this, just the logical structure of this, right? This is saying that one condition, which I want to call P, implies another condition, which I want to call Q. So we'll call differentiability, we'll call P the claim that F is differentiable at A, we'll call Q the claim that F is continuous at A. So using these symbols, and this is just the tiniest crash course on symbolic logic, which is a huge field, but there's a little course on it, right? This theorem, the 3-minute mini course in symbolic logic, you could write this theorem as P implies Q, right? And the little arrow indicates implies that this condition causes that condition. P, under the condition of P, we can conclude Q. So this is a very common thing that you ask whenever you see a statement of the form P implies Q. It's very common to ask, is the converse true? What is the converse of an implication? The converse is Q implies P. Right, so we have we have P implies Q. We know that's true by the cute fill in the blank proof in my textbook. It's a great question to ask. What about the converse? Is Q implies P true? So what would we be asking here? We would be asking, can we conclude differentiability, right? Condition Q, differentiability from continuity, right? That's another way to ask this question about the converse, right? So does continuity imply differentiability? Does continuous imply differentiable, right? That's another way to ask this. So, and sometimes you'll hear this word, converse, or you'll hear it, I think, more often actually in as a descriptor. You'll hear people say conversely, right? Sometimes you'll hear people say things like that in maybe in formal settings, in courtroom settings or something like that, right? You might hear someone say, if the defendant pleads guilty, say you're talking about a plea bargain, right? If the defendant pleads guilty, then he will receive a reduced sentence. And conversely, if he does not plead guilty, he will not receive a reduced sentence, right? You'll hear these sort of discussions, right? And conversely, if his sentence is reduced, it means he pleaded guilty, right? You'll hear that word conversely to mean that the cause and effect goes the other way from the claim that was just made. So just a tiny bit of logic there as we're talking about these ideas from calculus, right? Now here is an example of this. So I claim no, and here the converse does not follow, and here's why. Here's an example. Consider this function, I want to consider f of x equals x to the 1/3 power, right? So, or cubed root of x, you can say it either way, right? So what is this? Well, this is the inverse function of x cubed, right? So imagine that classic parent graph, x cubed, okay, it's like this, right? It's a one-to-one function, it's invertible. You don't have to restrict the domain at all. So now take that and reflect it about y equals x, and you get a graph that goes like this, right? So this is the function f of x equals cubed root of x, right? So I want to consider this specifically at the point x equals 0. Right? Here, I claim that it is continuous. Right? It certainly is continuous. If you imagine tracing these y coordinates towards as x approaches 0 from the right, or you imagine tracing these y coordinates as x approaches 0 from the left, right? It's pretty clear that as x approaches 0, this function, you can even just see from the graph, this function approaches 0, both from the left and from the right. The two-sided limit exists. Now, does the function exist at that point? Yes, this is just 0 plugged into the function cubed root of x, right? X equals 0 plugged into cubed root of x. There's our dot, right? So this is saying that the limit and the value of the function, they're both real numbers and they're the same real number. They match, right? This is our definition of continuity. So yes, it is continuous. But I claim the derivative at that point does not exist. Graphically, if you want to kind of see it off the graph, you could say, hey, look at the tangent line, right? The slope here, what would the rise over run be? The rise could be absolutely any quantity because the line goes up and up and up, and the run is 0, right? There's no run to that line. It's a vertical line. So you could say vertical lines have undefined slope, or you could say for the slope infinity, but you could equally say the slope minus infinity, right? Because it also goes down forever with no change in run, right? So it's hard to say whether it would be infinity over 0 or minus infinity over 0, or if the slope would be infinity or minus infinity, right? So it's that's why we have to just say d and e, right? We would just have to say that the derivative at that point does not exist. The slope of the tangent line is undefined. So how can I verify this? I can verify this by just try to calculate it, right? If I did f prime of 0, what would that be? It would be the limit as x approaches, the limit as h approaches 0. Right, I'm using my definition of derivative here. And this is garbage. Why did I say x approaches a? H approaches 0. I hope at that point of the video you went, what is he talking about? This is right. This should be h approaches 0. Right, h is going to 0. The run, we send the run to 0, and then we look at the slope of the corresponding secant line. So I'm going to use this definition of derivative, right? And I'm going to say, okay, I have the limit as h goes to 0, and this is going to be the cubed root of 0 plus h, right? That's plugging a into that definition, minus the cubed root of 0, right? Because a equals 0 in this case. Down here I have h. So this is the limit, and this actually cleans up really nicely, right? If I the second term is just 0, right? And so this is cubed root of h minus 0. So this term goes away completely. So cubed root of h over h. So this limit what are we always hoping for when we do the limit definition of the derivative? We're always hoping for that h to cancel. That's what removes the discontinuity, right? That's what resolves the discontinuity here, resolves the division by 0 and gives us a function that, or gives us a limit that exists, right? So, but here, look what happens. Consider this top as h to the 1/3 and the bottom as h. Well, then what does this become? This becomes 1 over h to the 2/3, right? You subtract the exponents because when you subtract the exponent, when you have a quotient with the same base, right? Think of it as h to the 1, h to the 1/3, 1 minus 1/3 is 2/3. So I'm doing that cancellation, the difference of the exponents. Well, now I'm just kind of stuck. There's nothing more to do. There's no more factoring or canceling, or there's really absolutely nothing else to do here, right? This is as simplified as it can get. And if you look at what we have, I don't have something indeterminate and strange where I can't really tell. Like say this is 0 over 0. So I can't really tell what's going on until I've simplified it more, right? This is not indeterminate at all. This is an extremely tiny positive quantity, right? Because whether you plug in an h like 0.1 or an h like negative 0.1, doesn't matter which side of 0 you're coming from, it's getting squared. It's h squared, and then you take the cubed root of that. So it's always a small positive quantity. So this goes to infinity, right? This limit is infinity, which in a sense matches the picture, but we would not call it differentiable at this point, right? Because the derivative did not give us a real number, right? So here we have, we see why continuity does not imply differentiability, right? We have this theorem that says that differentiability does imply continuity. Here we have an example of a function that's continuous at the origin, but not differentiable. Therefore, the converse is not true, right? We cannot say that continuity implies differentiability. So that's a little theorem relating some of the key ideas in calculus. An example showing us that we cannot, in the theorem, we cannot say that a function is differentiable if and only if it's continuous. Can't say that, right? That would be too strong of a statement. So it also shows us how to draw our little diagram here, right? It shows us that we can actually complete this diagram like this, right? That if a function is differentiable, it's necessarily continuous. So the class of differentiable functions lies properly inside the class of continuous functions. But you would have things like, so you'd have things say like e to the x, which is both differentiable and continuous everywhere. You'd have functions like cosine of x, which is both differentiable and continuous everywhere. X squared is differentiable and continuous everywhere. But then out here, outside the differentiable circle, out here in the continuous area, you would have a function like cubed root of x, right? The example we just did, which is continuous everywhere, but it's not differentiable everywhere, right? So this is how you can look at that kind of diagram. Of course, there are also actually plenty of functions, many more functions that live out here in the neither camp, right? So, out here you can have, say, functions like say, 1 over x, right? 1 over x is, it's not differentiable at 0. It's also not continuous at 0. Or, you can have far more pathological things, right? Functions that are nowhere differentiable or nowhere continuous. So this is our analysis of this situation. So this theorem shows you that this theorem, along with this counterexample, shows you that the correct way to diagram these concepts, right, is that the differentiable functions, that's our this is our the avocado pit is the differentiable functions, right? And then the out here, the flesh of the avocado is the functions that are continuous but not differentiable. Great, thank you so much. Fun ideas from